Welcome to the Explainer. Okay, I want you to imagine a super relatable scenario. You just ordered a pizza, you're starving, and you're staring intensely at your smartphone, watching that tiny blue dot representing the delivery driver slowly inch its way onto your street. It feels so incredibly simple, doesn't it? I mean, it's just a little map on a screen. But the hidden invisible reality behind exactly how that dot moves, it is absolutely mind-blowing. So let's dive right into this. You've got to ask yourself, why is your phone secretly a time machine? Seriously, think about it. Because to get that little blue dot to move smoothly across your neighborhood grid, your smartphone is actually, right at this very second, actively negotiating with a massive network of atomic clocks, flying 12,000 miles above your head in the literal vacuum of space. And man, here is where things get truly wild. Without the mathematical equations of Albert Einstein, that pizza wouldn't make it anywhere near your house. In fact, if we didn't actively account for the mind-bending physics of relativity, your GPS would drift off by a staggering 10 kilometers. That's over 6 miles in just a single day. Your delivery would literally end up 3 towns over. It's just crazy to think about. Section 1. Constellations in the sky. 30-plus navigation satellites. You know, back in ancient times, sailors used to look up at the stars to navigate. But today, our constellations are completely artificial. And this brilliantly illustrates the process of trilateration, which is basically using overlapping spheres of distance to pinpoint an exact spot. It goes a little something like this. Step 1. Those 30-plus satellites are constantly broadcasting their signals down to Earth. Step 2. Ground stations use radar to verify their exact orbits in space. Then step 3. Your phone acts as a highly sensitive receiver, listening to these signals and calculating the distance. Once it connects to 4 or more of these satellites, boom, step 4 happens. Your exact location is perfectly pinpointed. Now, when it comes to normal civilian operations, the accuracy is within about 7 meters or 23 feet, basically 95% of the time globally. But for professional and military use, that can be narrowed down to mere inches. The US government is carefully, constantly monitoring this entire system to maintain that incredible, absolutely crucial precision. Section 2, Einstein's relativity switch. Let's look at Einstein's physics. So there's this invisible mathematical mechanism that prevents our daily navigation from just drifting off the map into total chaos. And it all boils down to this one crucial concept: time dilation. The atomic clocks on these satellites measure time with unimaginable precision. We're talking about counting over 9 billion oscillations of a single cesium atom every single second. But here is the really wild part. They actually experience time differently depending on where they are. Okay, a classic physics analogy really helps make sense of this. Imagine space-time as a giant trampoline, right? And there's a heavy bowling ball, which represents the Earth, sitting right in the middle. Clocks down here in the deep warp of the Earth's gravity actually take slightly slower. But those satellites, they're sitting way higher up on the rim of the warp, where the fabric is less stretched out, meaning their clocks actually tick slightly faster. They are quite literally traveling through time at a slightly different rate than you and your phone are. No way, right? Section 3. Modeling the lumpy Earth. Discovering the true Earth geoid. Well, mastering the cosmos is really only half the battle here. You see, gravity isn't actually uniform everywhere. Why? Because the Earth isn't a perfect, smooth sphere. It is actually an irregular, kind of lumpy potato shape, scientifically known as a geoid. So to make GPS highly accurate, scientists needed a flawless, perfectly calculated mathematical model of the Earth's true lumpy shape. And that brings us to the monumental contribution of Dr. Gladys West. She is a true hidden figure whose incredibly complex coding and mathematical models of the Earth gave the physics a precise blueprint to actually work on. Without her foundational work modeling our lumpy planet, those satellites up in the sky would basically be flying completely blind. Section 4. The psychology of the click. Navigating attention. Now, just as GPS uses math to navigate physical space, digital content relies on psychology to navigate human attention. Specific numbers and titles can actually boost click-through rates by a massive 20 to 30%. Throwing in power words adds another 15%. Ultimately, it's all about creating a curiosity gap, like asking why your phone is a time machine in the first place, to really capture your focus and ensure you actually click to learn more. And packaging all of this is an art form in itself. The golden rule here is 1 + 1 = 3. Basically, your title and your visuals absolutely must work together to tell a larger story, not just repeat the exact same information. Taking really complex stuff like cosmic physics and mathematical models and turning it into a clickable, engaging format requires intentionally creating that perfect curiosity gap.
Section 5. A world without GPS. What happens when systems fail?
So, what exactly happens when this delicate dance of satellites, relativity, and complex math suddenly fails? The sheer scope of our reliance on this invisible infrastructure extends way, way beyond just tracking a pizza delivery. I mean, GPS provides the backbone for early warning systems for tsunamis. It monitors volcanoes and earthquakes. Global maritime shipping, commercial aviation, military defense, and literally the entire future of self-driving cars depend completely on this invisible signal. And honestly, the fragility of this entire system is a very real concern. On military and tech forums, users are actively preparing for the absolute worst-case scenario. One user emphatically noted, technology will fail when you need it the most in the harsh environment of combat, y'all. Professionals out there are already out in the field practicing with analog backups, like paper maps and old-school orienteering compasses, preparing for the very real day that the signal finally drops. Which leaves us with a final, really provocative thought to ponder. What happens to our hyper-connected, incredibly fast-paced world when the invisible lighthouses in the sky can no longer be trusted? It's such a fragile, beautiful system of math and physics that we blindly rely on every single day. Thank you so much for diving into this incredible explainer with me. Stay curious, and I'll catch you in the next one.